Hello and good afternoon. Ladies and gentlemen, I welcome you all to Tasking's webinar on linker scripting and strategies to reduce link and locate time, which will be the first part of the webinar series, Secrets of the Tasking Multiverse. My name is Bharat Koppa. I am a technical sales engineer at Tasking, and I will be the moderator of today's webinar and also one of the presenters. In the next 60 minutes, our technical marketing manager, Roger Smith, and myself will guide you through an introduction to the Tasking's linker script language, or the LSL, and explain some of the proven strategies to help optimize your build process and minimize link and locate time. Tasking is active partners with leading OEMs and tier ones, and we focus on safety critical and cyber secure software development on multi-core architectures. Tasking provides tools that can be used at different stages of software development. The Infineon Oryx Tricore tool chains are ASPICE Level 2 compliant and conform to ISO 21434 cybersecurity standard, and are TÜV certified according to ISO 26262 up to ASIL-D. We have been successful in receiving a TÜV certificate for our VX toolset for ARM as well, and the certificate can now be downloaded from our website. The Tasking performance tools, Embedded Profiler and Multi-Core Performance Tool, help you detect cross-core memory accesses and provide guidance on how to reach an equally distributed core load in your multi-core system. The Tasking safety and security ecosystem includes Safety Checker, which is a static analysis tool to ensure freedom from interference between different software components inside the ECU that have different ASIL levels. And the Tricore Inspector provides embedded system developers an automated method for identifying SIL 2, 3, 4 toolset related issues during the compile time. And finally, Tasking offers qualified C and MAT libraries as per ISO 26262. And the Pin Mapper, which is a hardware configuration tool, completes the portfolio. Some information about this webinar today. This webinar will be recorded and will be available on our website at the link shown below in the next couple of days. We also invite you to review our previous webinars, as well as our library of application notes, white papers, and tips and tricks videos. In case any questions arise during the webinar, we invite you to use the Q&A function on your Zoom console, and all questions will be answered at the completion of the webinar. Let me quickly introduce the presenters today, the speakers today. Roger Smith is our technical marketing manager with over 25 years of experience in designing and debugging automotive electronics. And in his previous role, he has spent 12 years as an application engineer supporting braking ECUs, EPS ECUs, and ADAS applications for leading automotive semiconductors. And myself, Bharat Koppa, I am an electrical engineer with over 12 years of experience developing and testing automotive embedded software. Apart from the presenters shown in the slide, we also have one of our very experienced application engineer as a panelist, Mr. Ulrich Kreut, who helped us put together the material that we will present. And he will take up your questions at the end of the presentation. So with this, I would like to hand over to Roger.
Thank you, Bharat, for the kind introduction. I'd like to wish a warm welcome to all our attendees. The Secrets of the Tasking Multiverse webinar series will focus on powerful toolset features, which can be a little intimidating to both novice and expert users alike. As an automotive ECU engineer with over 25 years of industry experience and support, automotive safety systems are characterized by the 3 R's: robust, reliable, and repeatable. For high-performance systems to remain repeatable, sensors, electronics, algorithms, software, and base systems must be calibrated. Let's examine why. If we look here at a very standard automotive use case, engine control, you can see we have a basic communication, we have some power supplies, we have a microcontroller, which in this example is going to be the RXTC27X. You can see a number of outputs over here where we have an ignition driver, which is going to drive our ignition plugs or our spark plugs. And we also have a half bridge driver here, which is going to drive our throttle. You can also see here a number of sensors which are inputted into the engine control ECU. And in this particular example use case that we're going to investigate today, we're going to be focusing on the throttle position sensor. So as previously mentioned, today's automotive safety systems require OEMs tier 1s and tier 2s to calibrate ECUs and sensors for optimal safe performance and precise operation and control. It can't be emphasized enough that finding an optimized set of ECU parameters is a crucial element for the overall vehicle performance. If you look at some of the typical engine calibration tasks, these include the optimization of base engine parameters and algorithms that are used for calculating injection, ignition, and valve timing. And these optimizations are also with respect to engine outputs such as power, torque, and fuel consumption. So if we look a little more detail into the throttle position sensor calibration, you can see here for reference, I've attached the actual a reference to a throttle position sensor. Now what the throttle position sensor does is it actually measures how open the throttle is, and then it uses this information to determine the correct air-fuel mixture. So changes in the throttle position will result in your engine controller modifying this mixture as well as modifying the ignition timing. So what happens if our throttle position sensor is not calibrated correctly? A number of things can happen. First of all, you can always get that very annoying check engine light where you don't know if it's actually something serious that's wrong or if it's a sensor failing a plausibility check. Your engine may not generate enough power. A perfect example of this is you press on the gas pedal and the throttle opens. However, the sensor reports that the throttle is closed, so no fuel is added. You have a very lean air-fuel mixture, which means that you have no power or less power. Other causes of not being calibrated correctly can be poor gas mileage. This is where we're just adding unnecessary fuel. You can also get car jerks, and you can get where it's unintentional acceleration. You can get a rough idle as well. All of these different situations here result in potential safety concerns and non-optimal performance. And so how can we correct this? Well, we calibrate. We make sure our sensor is calibrated, and then we have a repeatable performance with our throttle position sensor. So let's take a look now at how tasking plays in this. Let's look into the tasking toolset build process, which is shown here. And we're going to go into this in more detail in the next couple of slides. So if we focus here at the top here, you can see in this particular example, we're starting with a C++ source file. That source file is then fed into the EDG front end or our C++ compiler, which will generate an intermediate C file. This intermediate C file will go into our C compiler where our different optimization settings, both in the front end and the back end, which is part of the optimization process, which is not really part of this webinar here. But you can see what we'll get is we'll get a assembly.src file out of our compiler, which will then be fed into our assembler. And then the assembler will then generate a relocatable object file. And we're going to spend a lot of time in today's webinar talking about and examining the relocatable object file. So as previously mentioned here, we have our .out file. So what's contained within our out file? So we have information like the code size, the source file name. We have binary code and data, which is divided into different sections. We have imported and exported symbols, which you can think of them as functions or data objects. We have a list of locations with symbolic references. Now you'll see later on this slide here that the linker actually takes those symbolic references and assigns actual addresses to them so they can be placed within the memory map of the actual hardware device that you're using. And finally, you can have debug information can be optionally generated, for when you're going through and debugging your code. So now this relocatable object file is now fed into our linker locator. And this is where the majority of our talk today is going to focus. So when we look at the linker locator, what it's going to do is it's going to scan all the specified relocatable object files in libraries. So you can see here I've added an .o file 2 here, and we have the relocatable object library. This is a very important aspect, and there will be future webinars in the future on this topic. Basically, a library is a binary collection of object files, which can greatly improve the efficiency of your build if you utilize these libraries correctly. The linker will then combine all of these sections after processing all of these source files into a single section, assuming that you use the concatenate sections option, which we'll be discussing later on in the webinar. So hopefully that becomes part of your process. The linker will then write these results to a .out or a single relocatable linker object file. Or the alternative is that it can keep processing during the locating phase if some of these references above haven't been resolved yet. So if there are unresolved references, then you can link additional object files and archive files to resolve those remaining unresolved references. And the final step of the link locate process is to generate the selected output binary type. So you can see by default, we generate an ELF file. The ELF file contains an image of the executable code as well as data, and it can contain debug information or symbols. You'll also see here that one of the things that the linker and locator does is it generates also a set of resultant files, which, as you'll see in this discussion and that you've seen in previous webinars, is the value of the map file. We can't encourage you enough to use your map file. It's very helpful, very helpful. So now, how do you control the link locate phase? Well, you control that via the linker script file or the .lsl file. And here I'm going to hand it back over to Barath where he can continue this discussion.
Thank you. Thank you very much, Roger. Okay, so let's say you decide on using an Infineon Oryx for your throttle control ECU. And let's say the software architecture of the throttle control ECU is in a way that the safety critical modules coexist with non-safety critical ones. It could be necessary that you place safety critical code and data in different partitions. And before we learn more about how to do this, it becomes necessary that we know more about memory segmentation. Memory segmentation is a process in which the main memory of the computer is logically divided into different segments, and each segment has its own base address. The Infineon Oryx Tricore also has its own addressing method or memory map, and the Tricore CPU is a 32-bit CPU, and this table shows how the addressable 4 gigabytes are divided into different segments. There are some segments that are unused or unavailable to the user, which are marked as reserved, and the other ones are available. And for example, let's take an example of DSPR0, the data scratchpad RAM 0, which is local to core 0. And this is located in a segment which begins with the address 0x7. And the cached pflash begins with the address 0x8. And the non-cached access to pflash is, and this segment begins with the address 0xa. And all these segments can be addressed as near and far. So let's take an example of data scratchpad 0 again. The first 16 kilobytes in the segment are addressed as near RAM, and the rest of the memory is addressed as far RAM. The difference between near and far addressing in a nutshell is that fetching variables from a far RAM requires 2 assembly instructions more compared to fetching a variable from the near memory. And this was explained in a great detail in one of our previous webinars, Secrets of Oryx Multicore Performance. And this webinar is available on demand on our website. And if you would like to know a little bit more about near and far addressing, I encourage you to watch this video. So let's have a look into the contents of the linker script file. A linker script file is added to your project when you create a new project with the VX toolset. And this file is normally empty, but it includes an LSL file, which is the Oryx variant specific LSL file. And this file has information like the size of the DSPR that's available on the chip, or the LMU, program flash and data flash, etc. And we recommend that while you're working with linker scripts that you turn on the outline view as shown here. And we recommend this because it's a graphical view, and it represents the contents of the LSL file graphically. And let's say when you click on one of the attributes that are shown here, it will take you to the line in the LSL file where this is defined. For example, I clicked on pflash0, and then it tells me, okay, pflash can be addressed as cached between from the offset 0x8000, and it has a size of 2 megabytes, and similarly has a size of 2 megabytes and can be also accessed as non-cached, and so on. So now let's say, okay, so let's, as explained before, in order to get ISO 26262 compliance, you may have to place your code and data in different segments, in different partitions. And let's see how we could place code in a particular segment. So here I have taken a simple example of a function which is updating an array. And when you compile this code with the tasking C compiler, it generates code and data in different types of sections. And the compiler generates different prefixes for different types of section. In this case, for the code section, a prefix .text is generated. And let's say we want to locate this function at an address or at an offset of 2000 in hex from the beginning of the pflash0. This can be done by specifying a group. So here I have a group called picflash, and I say that it should be located in the program flash and between the offset 2000 and 3000 in hex. And then I have to select the function which has to be located there. So in this case, I select the function main. So you see the function main is selected here, which is there in the pflash function module or the C file. So the function is there in the pflash C file, and then I select the prefix .text. And when we run the linker, so then a map file is generated. And when you look into the map file, there is a picflash group and a section, and in the section you see the main function is located at the address 8000.200, which was actually specified in the LSL file. So coexistence of elements with different safety levels also require that you place variables in different partitions. And this is especially important because you have to make sure that a non-safety critical module doesn't unintendedly modify a memory address in a secure block. So now let's have a look on how to place an array at a desired memory location in the RAM. So I take up the same example, except for the array is now being updated by a constant value 9, and I call this far. This is a far variable. So just to repeat what's far and near RAM, the near RAM refers to the first 16 kilobytes of the segment, and the far RAM refers to the memory which is beyond the 16 kilobytes. And it's also worth noting that you could use the keyword far and still locate the variable in the near memory, but the other way around is not possible. So if you have a near variable, you cannot locate it in the far region. So as explained before, the compiler generates different prefixes for different types of sections. And for the far variable, the prefix .data is generated by the compiler. Now, let's say we want to place this in the data scratchpad 0 of core, associated with core 0, and in between, an offset of 5000 to 5500 in hex. Then we specify that it has to be located in DSPR0 while we are creating a group of named pick data. And now we select the right variable inside this group. Again, we select from the data section and from the module pflash function, which is a C file, we select the variable test. And when we link, we see that in the map file, there's an entry for the variable test, and it is located at the address 5000 from the beginning of the data scratchpad. What you have to note here is that you're using a range, and it could be that your variable is placed, has an address anywhere in between this range. If you want to locate a variable at a particular address, so you just specify one particular address instead of a range. Okay. So now let's have a look into uninitialized variable. And these are the variables that are available in the .bss section. And these variables are cleared at the startup. However, no initial values are assigned to these variables. And this has to be normally done by the user in the application code. However, for the data section that we talked about briefly, variables are initialized with fixed values. And now the question, where are these initial values located? So if you look into the map file, you see that the variable test is also available on the p/0. And this is where the initial value of 9 is stored. And let's see how how the values are now copied. So when you turn on, when you power up the microcontroller and you run the you run the initialization code, the startup code, and in the startup code there is a copy table which does the update, which copies the initial values of the variable from p/flash into the DSPR. Going back to the throttle control ECU, say that there are calibrations that you have defined and you are calibrating a sensor while you are driving uphill, and you are tuning a sensor to get the right air fuel mixture. The calibration tool normally updates the values in RAM during runtime via the XCP protocol. And let's understand how these calibration values are loaded into the RAM. The calibration values are normally stored on the p/flash or the data flash, and these have to be loaded in the RAM by the user. The user could now make use of the overlay functionality, which the linker supports. And here we define two groups, one for the RAM and one for the ROM. And as the constants are normally, as the calibration values are normally constants, they are assigned the prefix of .ro data. And when we select the same variable test, in the overlay part and also in the ROM part. And normally when we have different groups, then the linker generates constants or labels which depict the beginning of the group and the end of the group. But what we have to make sure here is that application code is now responsible for copying the initial values from the p/flash to the RAM. So just to show you, here in this code snippet, I could just show you that there are two linker labels that are generated. I have one for the flash and one for the RAM. And the RAM is the one which is in the DSPR0, and the flash is the one for the p/flash. And I have a for loop where I'm copying, the initial values of variables from the p/flash to the RAM. And so this step has to be done manually by the user. So from p/flash to the DSPR. And just to complete the story, so what happens then to the calibrations? The calibrations, you calibrate the application could then calibrate the value in the RAM, and then during the end of the drive cycle, when you turn off your vehicle, and during the shutdown phase, the constant the value in the RAM could then be updated in the data flash. Or it could be that you create a data set out of from the calibration tool and create a new hex file and reprogram the MCU. And this means that in the next drive cycle, the calibrated value is now available on the flash, and it's copied to the ROM. I hope this was interesting. Thank you for your patience, and I will now hand over to Roger.
Thank you, Barath, for that nice introduction there on our linker script language. So clearly, engine control is an automotive safety application. And with it being an automotive safety application comes along the requirement to use AUTOSAR. And AUTOSAR, or the Automotive Open System Architecture, provides a standard interface, between your application software and your hardware, so that your higher levels of software can be independent of your microcontroller. So if we take a little bit deeper look into this, you can see here from the application layer, we have our, electrical power steering, our autonomous cruise control, or our throttle position sensing type hardware applications. Down here in the AUTOSAR basic software section, we have our communication services and our abstraction layers. If we take a look at the overall AUTOSAR stack, you can see again, the application software is located in the application layer. The AUTOSAR basic software is basically contained here between the runtime environment and your abstraction layers for your microcontroller, and then your hardware is down here in the microcontroller section. So just to take, in terms of our particular application, our throttle position sensing function would then be in the application layer. In the RTE, we would have our middleware layer providing our communication services. We would have our memory and diagnostic services. In this area of the stack, we would have our ECU abstraction layer, and then the MCAL abstraction layer, or the microcontroller, abstraction layer being the lowest software layer. And again, it's designed to make software appear be independent of microcontrollers down here. In the end, all of these puzzle pieces, what do? They increase, the size of our builds. We have source files. We have now RTOSes. Our binary sizes are getting larger, and consequently, our build times are getting longer. And so what we want to do is let's look at a couple of example customer use cases, and then let's go through a couple different strategies here to try to understand how can we make our build processes more efficient and shorten this link and locate time. So one particular OEM, I'm not going to share any of the details. They're a consortium-based development team, so they've experienced a 3-hour plus build time with an 1 and 40-minute link time. Clearly, making a simple change in code and having to wait 3 hours in order to test it isn't the most efficient process. And so, let's try to help out our customers here with this. And, that this webinar is intended to do that. I would like to say, based on the previous slide, when we looked at project complexity, that link times between 3 to 5 minutes are not always unreasonable. And so let's keep that in mind as we're building, what is the complexity of your project. The key point is that each one of these automotive projects is unique. These cases need to be analyzed and optimized individually. And it's not making a simple correlation like, oh, I have a large ELF file, therefore I'm going to have a long link time. These are not true, as this use case will show. And so here's an example here where the customer is, hey, it's taking 7 minutes to link my project. This is unacceptable. Tasking, please help. Our first question is going to be, well, hey, what's in the size of your project? And you can see the details of this project. This particular customer has over 2,000 constants, over 11,000 functions, 2,000 plus initialized variables, and 1,100 plus uninitialized variables. So this is a fairly complex project. And in the end, a 7-minute link time may be acceptable, or that may be what's expected for a project of this nature. To further this, let's look at a couple of additional customer use cases, and we're going to look at these, the performance, or how the performance of these use cases change as we look at some of these different strategies for improving our link locate time. Now, these are customer use cases. They are proprietary. I cannot share source or symbol type information or who the customers are. But what it does do is it does give a good representation of how some of these strategies can help. And if you're not aware of what all these strategies are, stay tuned. We will talk about them shortly. So we will look at map file content. We will look at unreferenced sections, the first fit decreasing, linker optimization setting. We talked a little bit about copy tables and compression. And so there's also some additional strategies that we will discuss. So if we look at from a worst case representation, this is kind of, let's build with everything enabled in its worst state, with these two particular use cases. And what do we see? So in use case 1, we see a link time of 4 minutes and 32 seconds. And you can see an ELF file size here of, this is measured in KB. So this is 820 meg. Here is this ELF file size. And here you can see we have a 35-minute link time with only a 327 meg file. So you can see right here that the correlation between ELF file size and link time is not true, or there is no correlation. So now let's get into the meat of the webinar, and let's start looking into some of these different strategies and what they entail. So the first strategy is going to be simplifying your LSL file. So a long link time can be caused by a large and complex LSL file. To reduce this linker time, you want to simplify the LSL, and you want to minimize the conditional statements to avoid multiple iterations of the link locate phase. And so I've shown here just a couple examples. Here's a simple LSL over here. You'll see we have a section, a group, and we're reserving an area. And over here in what I call the more complicated LSL, as you can see, we've introduced wildcards into the LSL, and we've also introduced some if else type statements, and the largest impact to your link locate time is going to be on the number of these conditional if statements, because the if statements basically cause your linker and locator to recursively go through and try to relocate things based on these ifs, because as we'll learn very shortly is that the LSL file processes from top to bottom, and so the order of these commands in the LSL file are very important. What we'll also notice here is that, or that we'll see, is putting wildcard selections at the end of the LSL will actually reduce the number of sections that the wildcards need to process, and can also help to optimize, your overall process. We will like to point out that if you are using an AUTOSAR OS, the LSLs are very often generated by the OS configurator tool, and may not be alterable or maybe not recommended. And so there is, some difficulty, obviously, in this process, and tasking is here to help. And we'll say how, I'll explain how we can help at the end of the webinar. So let's look at a simplified LSL example here, where we're looking at, what happens if we place wildcards near the top of our LSL file. So I have a very simple C source file here. You can see we have 6 variable declarations, 3 chars, and 3 integers. And you can see that they've all been, given some names here when we define them. So when we go through our tasking compiler, here's that SRC file that I talked about in the beginning, and you can see we have our, as Barath kind of highlighted in the previous discussion, we have our label here that the compiler generates. And now as soon as we introduce our LSL file, which is again going to be processed from top to the bottom, what actually happens with our linker. So the first thing is that as we're processing down, is we have our group my data 1. Our very next thing is that we're looking for a BSS file called variable1 unsorted. And so let's go through the list of unlocated sections, and sure enough, we find it. And so it's placed here. I would like to point out, however, that, the AURIX is an even address based machine. And so a char is only 1 byte. And so we do need a stuff byte here in order to maintain that even address within memory. Going down to the second line of the LSL file, we're looking for the file, the section variable2 sorted. We find it, so it's placed. Easy so far. However, when we get to the third entry, you see we have a wildcard. And so as soon as you see the wildcard, the linker now is to check all the remaining unplaced sections to see if they meet this wildcard criteria. If we look over here at our 4 remaining files, notice they all have the same name. They all have var _*. So all of these files here basically meet this requirement. And so now the linker must go to a secondary placement protocol. And what it does is it prioritizes on alignment. And so that means that the integers are going to be placed first. So you can say as we continue processing, now var4 here, which meets the asterisk condition, is an int, so it will be placed next, followed by the next int, which is var6, which is then going to be followed by the characters 3 and 5. And if we go ahead and we look at our map file here, you can see that this is exactly what happens. But if you look here, notice we have a problem. And the problem is that when the user originally specified the LSL file, they wanted these files here to be contained in the group my data 1, and they wanted these sections here to be placed in my data 2. However, by placing this wildcard up here high in the LSL file, these sections right here actually in my data 2 met this requirement, and so they were placed in my data 1. And so that's where it's very important to to control the order. And you can see here by just simply moving the wildcard to the end, now we result in having our sections basically belonging to the groups as how we originally intended. So if we go to strategy 2, very simple, don't mix data. And so you've seen this table a lot, and you've seen this table a lot because it's extremely important. And you're actually only seeing, you can see this table here is shown in section 1.12 of our user guide. This is only a third of the table. And so there's so many different memories, and there's within the AURIX that there's 18 to 20 of these different naming prefixes. And so, know this table, I guess it will help you to understand what's happening when you're creating your LSL file and when you're going through and reading your map file. What we want to try to do is for an efficient build process is we want to try to keep our data or our initialized sections and our uninitialized sections separate or not intermixed together. So you can see in the first example right here, we basically intermix them together. The better approach here is to keep them separated. And why is that? Because we can reduce this copy file, this copy table size, because now the linker can group these together, and it can do one entry to initialize or clear multiple sections rather than having to do them all individually. And this next example right here will very clearly show that. So what's one of the secrets of the multiverse here? And that's this high-level object dumper. So the HLDump TC executable, it is located in your compiler bin directory, and it is very useful for extracting information about absolute object files. So if you're interested in playing with it, I recommend that you go use it. It's one of those little details that you have to deep dive the user manual to learn about it, but it's definitely a very powerful tool. So you can see here we have another example, another simple example. So I have 8 variables here. You can see I've intermixed here whether they're initialized or uninitialized, and they're all of int type. I've created an LSL file here that has both a bad order and a good order. And you can see here in the bad order, we're actually intermixing here the data versus here in the good order, we're grouping it together. So now let's go ahead and look at what happens. So the first thing that I've done for your reference is I've attached a control program invocation statement. So you can basically, this is just a command line command, for lack of a better word, so that you can go ahead and build your L file. And then here you can see how to invoke the tasking object dumper, and it's going to basically output here your copy table. So if we go ahead and look at the copy table, so this is what the copy table here for the intermixed data section looks like. So now let's take a little bit deeper dive here into the copy table and what is it telling us. So you can see here that we have a address label. If we again reference the map file, you can see that it specifies, that address label and where it's located. And so it's located here at the 3C. The next thing that you'll see is that if we look at our variables here, we're only going to look at a couple. So variable 1 and variable 2 here are going to be used in this example. And so you can see the address. So you can see the next copy here, the next entry of the copy table is going to be the start address of the range to be cleared. This next set of byte here is if you're copying data from Flash, it's the start address of where that data is located. Since we don't have any data and we're just doing a clear, this is zeros. And then you can see this next field here is going to be the number of bytes that are processed. Since we do have an int, we're going to do, the int type is 4 bytes, and then we're going to do a clear. If we go and look at the second line here, you can see var2 located at 80C. So that's our start address here is 80C. We are trying to move a value of 20. Brath explained how we have constants and how both pflash and DSPR are used in the earlier part of our webinar. So you can see that the pflash address is 80000024. So you can see that's our source address. And then the amount of data being copied here is 4 bytes. But you'll see what happens now is that since for each one of these variables here, we have our own separate line here. So we have 4 4-byte clears and we have 4 4-byte copies. If we go ahead now and look at what happens if we invoke the good ordered LSL file, you can see that this is reduced to 2 copy table entries where we're actually doing a 16-byte clear and we're doing a 16-byte copy. So this helps to do many things. It cleans up your memory. It allows your C start routines to run more efficiently. It reduces the amount of work of your linker. So it just overall improves the, the efficiency of your build process. So definitely try to separate your different data types. So moving on to strategy 3, disabling copy table compression. And so the linker, as we've shown, is it creates a copy table, and this copy table, it contains the start address and the size of all sections to be initialized by the startup code. By default, this copy table is compressed. And that means that the linker will go through and group sections that need, to be initialized. It does that in succession, and so that we can take advantage of this larger block, like we showed on the previous example. This does result in fewer copy table entries. It does result in a smaller copy table. However, it does require link time, right? Because now it has to go through and it has to process and it has to make decisions. And so like all engineering problems, there's a trade-off. So you have to trade off between having nice, clean, well-organized memory with not a lot of gaps versus having, a reasonable link time. By disabling the copy table, you basically, the copy table compression, sorry, you force the linker to place ROM copies of initialized and uninitialized sections as they're processed. And again, this results in a shorter link time, but could negatively impact the size of your copy table. And the last key point here is that this copy table should be located after all of the initialized sections are placed. A bad LSL file can easily result in gaps following the copy table. And so that's why, you want to place this copy table at the end of your memory. So if we go back to our use case here, you can see that by disabling this, the copy table compression by disabling it, so we're basically enabling it now. You can see that the link time here has been decreased a significant amount here, and you can also see the difference in the use cases, right? So the LSL files in each one of these cases were different. So you can see here it's a relatively small impact of change by implementing this particular strategy. But you can see in the second use case, we've gone from 35 minutes to 23 minutes, which is just a substantial improvement. So there's going to be 7 main strategies. So we're halfway through. So if we look at removing unreferenced sections, in some applications, like the Infineon ILLD is a perfect example, there's no library creation. So all of the RX peripheral drivers are built, which means that the linker must locate all of those sections. That's whether they're used or unused. And this leads to unreferenced sections. So there is a linker optimization called remove unreferenced sections. And what this will do is this reduces, memory usage by removing these sections. So a couple of examples of what this means is, so if you're using an archive, only sections referenced within your code are going to be extracted from the library. So we're not just going to place the whole archive file. Another example is object files, which do not include any global symbol definitions needed by your application, also aren't included. I think it's fairly intuitive, but these unreferenced sections, they lead to a potential waste of microcontroller memory. This can possibly lead you into a larger device, or it can lead you into not meeting your OEM specified memory overhead targets or requirements. So a handy little tool to keep in our back pocket. And if we go ahead and we see the effect of this on our overall use case, you can see there was another 6-minute improvement. What you'll also see, however, is that our ELF file size here did decrease, substantially here in this second use case. So I would like to show you an example here regarding removing unreferenced sections. So I've taken basically a screen capture here of our tool set, and you can see here within the main, we're basically, all we're doing is we're doing some watchdog work here, and then we're just doing a hello world. And you can see over here, you can see all of the ILLD directories. So all of these directories and folders have source code associated with them. And if we go ahead and if we build, and you can see that the delete unreferenced sections is not enabled. So when we go through this process, we will basically create an ELF file here. And if we look at the size of our L file, it's basically 28, it's a little almost 29 meg. And you'll see that our map file is, almost 9 meg. So very, very large files. Doing something as easy as just enabling, deleting unreferenced sections. Look at, we've basically taken a 29 meg L file down to 9 meg, and we've basically taken a 9 meg map file down to 2 meg. So what I did is I went through our map file and I looked at all the removed sections here, that we actually removed with this section, and there were 6,190 sections removed. So you can see just by not clicking that box, right, you could have placed, over 6,000 objects that you don't care about, your application isn't using. So why are we doing that? So another handy thing to keep in our back pocket. If we look at strategy number 5, this is reducing the number of sections. I think it goes without saying that the more sections the linker must place, the longer the link time. And by default, the linker does not merge sections with the same name into a common named section. And you'll see that here if we're not using the concatenate sections here. I'll show you actually on the next slide when of what this would normally look like. So if you look in the user manual, you'll see there's a concatenate sections option, which we can add in this additional option. If you look at the map file, you can see that we have individual sections here. So this block queue task, we have 8 different objects or sections that are created with the same name. And if you go and look in memory, you'll see that they're not placed contiguously within memory. So we have one block queue, which has an offset or at an address of 66F4. And then we have a bunch of additional block queue sections, which are placed at 6784, which address, which are now contiguous. And what this means is when you think about your block queue task working, it's got to hunt around in memory for the pieces that it needs in order to do its job. And so it's just clearly an inefficient way of doing things. You can see here by just adding this concatenate section, what it did is it took all of these sections with the same name and it created one object with that name. And then you can see when it placed it in memory, it placed it all together in a contiguous block. And so now, it's very easy to find your code or your sections are easy for your application to locate because they're all they're all next to one another contiguously within memory. So faster locating due to less sections. So we have 2 sections or 2 strategies left. This one here is one that touched home with me. And so there's the map file, which as we've highlighted is an output that contains information about the sections and symbols. What I didn't know though is how customizable this was. And so when you go into the tool set, you have the option of generating either an XML or a map version of the file. Clearly, you wouldn't want to do this because the linker needs to take time to generate both of those files. And so you can skip it all together, or you can disable one. By disabling the XML map, you do provide a reasonable time save. You can gain back link time again by reducing the contents of the map file. So I've inserted here a snippet from our user manual, and you can see the default map file format. And so you can see we contain a lot of information, but do you really need all of that information? Do you really need to take, build time every single time that you're trying to do a build to create all of this information if you're not looking at it or if you don't need it? Key information, clearly the call graph, symbols, where they're located in memory, the locate results. Things like the link details, is that really important? Probably not so much. So what I've done here is I've, from the command line, you can actually specify which sections of the map file that you want, or you can also do that from within the GUI. I've just showed here that in this particular build, so we're gonna add call graph data, invocation data, locate and overlay data, and we're gonna remove the link data. And then if we go ahead and if we look down here again at our results, you can see there's a further improvement here in our link time. So, not everything is going to be a huge fix, but, you also see here that sometimes things that you don't think are going to have that big of an effect actually do reduce your link time substantially. In this case here, so we removed the bug information, and you can see the effect that removing debug information has on your ELF file size. So substantial effects. And so if you don't need the debug information, don't include it. And the last thing here is by not using map files, you can see that we gain almost another minute here, where now the linker doesn't need to generate that file. So the last strategy that we're going to look at is called first fit decreasing. And so by default, the linker optimization level is -01. And what that basically means is that the linker will fetch sections from the object file and place them from either low to high memory or vice versa, depending on how your LSL section layout header is defined. More information on that is contained within the user manual or within the user guide. Now, if physical memory is fragmented, it is possible that you have a section that is smaller than the available physical size, and it won't fit in the area where you want it to fit. And so what I mean by that is that say you have a section to be located, and it's larger than the remaining memory in a segment. And so what's going to happen now is that that section and the subsequent sections will basically skip over that gap and basically place it within the next memory range. And what that does is that leads to gaps in a waste of memory, throughout your memory map. So what you can do is by enabling this first fit decreasing optimization and relinking your application, what happens is the linker is going to place the largest sections in the smallest memory ranges where they'll fit. And then those smaller adjacent sections here within your memory are located last, and will fit in these remaining gaps. And you can see here that for this test case here, it actually went the other way a little bit. So in this particular use case, we gained 5 seconds. In this particular case here, we actually went up by a minute because, this iterative process here takes time. And so again, this is highlighting the trade-off. There is one final test case which I didn't include in the table, which is actually a very interesting piece of data. And so I haven't showed you the complexity of these LSL files. And so you have no idea of knowing what they are. But if you look back to the previous discussion with Barath, he said that you always start off with your RX variant, which basically defines your memory map, what the offsets are, what the sizes are, et cetera. And then you can add your own code below. So in this 35-minute here use case example, what we did is that we built the project with just the minimum RX variant. We didn't include any of the extra, groups and sections, et cetera. And we had a link time of 8.5 minutes. So you can see that we lost 27 minutes there in link time, which has to be observed every single time that you build your product or project based on stuff that you added. And so it is very important. The strategies are very important. And so, so that would be our main message here. So now we've gone through a number of these strategies. There are some other miscellaneous good practices here, which can also help to optimize your process. And so the first, as we kind of highlighted already, is that removing debug information that you don't need is very useful. So by using this strip debug linker option, you don't place debug symbols that you don't need. If you're using a well-tested and used legacy, object file that's been used in many different applications, why are you building it with debug information? You don't need to debug it. It works. And so why take up that extra space? And so this is another option here of just controlling, creating an efficient build process. The second good practice is that if you're using the 64-bit version of the toolset or 6.3R1, do know that patch 3 is available. This patch here specifically addresses long link times. And so if you're not building with patch 3, please contact either the support center or your local FAE. And then, we can get you information on how to get patch 3. And we can, and I'm going to highlight again how to do that on the last slide. Your virus scanner can be a major pain in the rear end. And so what you want to make sure, if you can, is to configure your virus scanner so that every single time we launch the compiler or the linker, we're not virus scanning that file. The other thing you want to do is you want to exclude the folders where tasking is generating files like the assembler files or the map file, so that you don't have to, every single time these files are created, you're not virus scanning them. In a quick way to verify that is you can use your Windows Task Manager, and then you can look at the Processes tab, and then you can look and see, is the virus scanner running, real time along with your build as you're trying to build your project. Another key point is that you can imagine, again, with these AutoSAR projects, that your overall project sizes can be gigantic. And so in several instances, we've seen them exceed 4, 5, 6 gigabytes. With a 32-bit version of the tool set, like 6.2 R2, memory errors are possible where you just can't finish the build process because the linker can't access, being a 32-bit tool, it can't access enough memory in order to do all the work that it needs to do. And so a quick workaround is to use the 64-bit version of the linker, and you can copy that LTC.exe from the 6.3 R1 folder to the 6.2 R2 CTC bin directory. That will allow you to now complete your build process. It won't, however, speed up link time, but you can at least, get a step further by being able to build your project. If you are debugging long link times, don't use Jenkins or a third-party, CI tool. Use the tasking linker command, and just to try to figure out exactly what's happening when you're debugging this your link time. If you are doing C++ work and you're using the --munch option, linker processing time could be increased due to the increased number of symbols. So just keep that in mind. And the last thing, which is really, really cool, is that for at least the compiler, you can invoke parallelization. And so you can use the AMK -J8 option. And let's say, for example, on your PC, you have 8 different cores. What you can do is you can actually, and you have 100 source files, rather than compiling those source files one at a time, you can invoke, up to 8 copies of the CTC, where you can do, you can build 8 files at the same time. So you can speed up the compilation process of your build. However, the linker does not support parallelization. And so, for the linker, it's just going to have to, there's going to be, you don't have this, this kind of secret of the multiverse per se to help improve the process, to improve your build time. So as we're wrapping up our webinar today, how to request tasking technical support. So clearly this LSL stuff is complex. And you can go through all the strategies, and you can read, all the application notes, and you can study the user guide, and you still may need help. Okay, so how do you do that? What do you do? So what you're going to do is you're going to initiate a support request. And there's multiple ways of doing this. So the preferred method is that if you go to tasking.com and you click on support and you click on support center, or you can go directly to the support center with this URL. You log in with your credentials, and then you're able to log a case. So the first question I know I'm going to hear is, oh, I don't have access, so what do I do? Well, if you don't have support center credentials, send an email here to our support team here at support@tasking.com. And the first thing they're going to do is give you access to the support center. So we can knock that one out right there. And then the third option, which is not preferred, is that if you go to tasking.com, you can click on this contact section right here, and then that will bring up a template where you can, input your name, customer name, email address, and what you're trying to do. That method is not recommended because it's not going to be a direct path to our support center, and so there may be a little delay in us helping you. Typically, we try to do next day support here, and so very reactive, and so please try to utilize these top two methods if possible. So when you're doing your support request, you want to definitely provide a copy of your LSL. As Barath already showed, that this is located within the project directory. Please note that with some of these more complicated builds, there are multiple LSL files. So please include all of the LSL files to help our experts get a better idea of what it is that you're trying to do. The next thing that you want to provide is that you're going to want to provide a copy of your text map file, and this is located in the debug directory. And then if you get a linker error, you're going to want to provide the details of the error, and you're going to want to provide what linker options that you utilized. And there's multiple ways of doing this. So if you provide your map file, there's a section at the top of the map file which lists all of your build switches or options. So that's one way of doing it. You can also provide, attach the build log or console log, which is located also in your debug directory. If you're running from the command line, you can add the --error- file, and then an error file will be the linker will generate an error file for you, or you can just copy the text from within the command prompt with the error message. And finally, you want to provide a nice description of what it is that you're doing. Are you in Windows or Linux? Are you on the command line? What's the version and patch of your tool set? Are you having a linker error, or are you just trying to reduce your linker time? And so that basically wraps up our webinar today. What I would like to highlight a couple of upcoming things here that Tasking is doing. So as we've seen today here, the Tasking linker can automatically place your code and get your application up running really quickly. However, for safe and optimal performance, you want to take advantage of this Tasking LSL, linker script language, and the map files. And so a LSL strategy application node is in process and will be coming soon. And so we invite you to stay tuned for that. The next thing, which is a very key point for us, is that there will be a webinar on September 22nd. And what the focus of this webinar will be is on the VX toolset for ARM. So we're releasing patch 1 of that tool set, and the added support, and that will add support for the NXP S32K3 general purpose MCUs. So I'm very big with expanding our safety ARM portfolio in terms of the architectures that we support. And the other thing which we'll be highlighting is the new TÜV Nord certification for our ARM tool set. And you can always go to www.tasking.com events to go ahead and register for that event. And the last thing that we'd like to highlight is we've also now received TÜV Nord certification for version 6.3 R1 of the tool set. And this is particularly important to you, the users, because that is the compliant tasking compiler version for MCAL 2.0. So with that, I will hand it over to Barath.
Thank you very much, Roger, for this nice presentation. And I would like to thank the audience also for your attention. You can follow us on LinkedIn. Please also have a look at the event section on our website for more upcoming interesting webinars and events. If you have any questions related to any of our products, please write us an email at sales@tasking.com, and one of our representatives will get back to you. Now let's move on to the Q&A. I see that there are a lot of questions. Okay, so let me take up the first question. Can this graphical representation of LSL, is the graphic representation of LSL possible with Oryx Studio? Roger, Ulrich, do you want to take up this question?
That's a good question. I'm not sure. I know with Oryx Development Studio that we have the tasking compiler is the framework compiler, but I also know that a number of features have been removed. And so, yeah, I'd have to look into that and get back to you. I don't know, Ulrich, do you know?
There is some kind of graphical representation, but I don't know what it's referred to. So when you open the LSL file in the tasking Eclipse, on the right-hand side, there is a window which shows some graphical representation of the memory. If that's what we are talking about, yeah, it would be, it is available in the tasking Eclipse environment. But honestly, I don't remember from the top of my head whether it might look different in the Aurix Development Studio Eclipse environment.
Okay. So let's move on to the next question. What is the difference between space address and chip address in the map file? Ulrich, maybe?
Well, it's maybe not explainable in a short term. So the LSL language itself is quite complex, but you do not have to dive into it that deep because it's separated into two parts. One part is about the architecture definition. That's something you don't need to care about because the architecture is defined by Infineon, and tasking is providing the LSL file for the architecture definition. So your playground is typically only the project-specific LSL file, which includes information for the section placement of your application code and data. So that's something which you have to modify typically, because otherwise the linker will just fill up the memory from lower to higher addresses. And the definitions in the architecture part of the LSL file, they include a space definition where it is defined which ranges can be accessed using near accesses, which ranges can be accessed using A24, EPS24 accesses, which is the first 2 megabyte of 256 megabyte segment, and which ranges can be accessed linear, which means that it can be everywhere in the address space of the tri-core architecture. And the important part, or the mapping definition, is done in the tasking LSL files, and the memory definition is also included in the derivative LSL file. But that's where the real mapping takes place. That means if you have a p/0 memory, you do define in which range this is mapped, and then it will start in segment 8 at offset 0, and also in segment A, because we are talking about cached access and non-cached access, and then you are physically accessing the same memory, but it is using a different segment number for this purpose. But this kind of information is included in the memory definition, where it goes to the real address space of the given on-chip memory, and also external memory if you want to add external memory to your application. But many applications are single chip applications.
Thank you, Ulrich. Moving on, any plan to share this presentation with participants after the webinar? So I think, Roger, please correct me if I'm wrong. So the presentation won't be shared, but the webinar video will be uploaded on the website. Is this right?
It's in discussion. So,
okay.
So definitely the video will be shared, and it's just a matter of managing logistics, I think. And so, yes, we will try to share the presentation.
Okay.
Worst case, you can always contact us at the emails provided, and then we can get you a PDF of the material.
Okay, so maybe the next question is for Ulrich. When you have a select statement with wildcards, will the data be placed in unreferenced section? For example, if you have calibration header marked between two stars, will place calibration header to an unreferenced section. Is that correct? And if so, why would it be?
I'm not sure if I got the question. So an unreferenced section, if you are, is a section which is defined in one of the source files, like you define a function or you define a global variable. And then if your application does not refer to that section at all, so the function is not called, the data is not accessed at all. Yeah, this is, from my understanding, an unreferenced section. And then we are talking about the linker optimization, delete unreferenced sections, which, when it's enabled, will remove that section, and it will be listed in the map file, which all the sections which are removed. So when you go to the bottom of a map file, then there is a list of removed sections which are not referred to at all. And if you disable this optimization, yeah, then your the linker output is still including the non-reference section, which means there might be dead code or dead data included in your application, which eats up memory space but is not really needed. But I don't get it at the moment what you refer to about this asterisk select and unreferenced section topic. If it's about if I select a section by select entry in with using asterisk, so I do not select it by its full name, will this section be automatically protected from this linker optimization? Then the answer is no. So the linker optimization, delete unreferenced sections, will remove a section which is not used and not explicitly selected by its full name in the LSL file. So that's one method of protecting a section from linker optimization. So when you select it by its full name without using asterisks, and really use the complete name of the section, then it will be protected from linker optimizations. If you are using an asterisk and the select will also select that section, then it won't be removed from, won't be protected from linker optimizations.
So I think this is a complex question. So I'm receiving more comments regarding this question. So what we would recommend is that you write an email to us with your specific query, or raise a support ticket, as Roger just mentioned in his presentation, and we would be happy to help you with your question. Okay, moving on to the next question. Does tasking offer a way whereby the autos are memmap.h and the linker can be configured via GUI? The purpose of the LSL is primarily for aligning sections of memory map. So to my understanding, so we don't have a tool which can do this. So of course you can look at the LSL file in a graphical view when you turn on the outline view, and it's also possible, when you right click on your project and go to settings, and in memory you can have a look at different sections as GUI, maybe make some modifications there. But currently we don't have a mechanism that can map the memmap and the LSL graphically. Okay, so moving on to the next question. Will you be sending these slides, or how can we get access to these slides? So I think this was already answered. We will have a look if we can provide you the slides, but for sure the webinar is uploaded on our website. So Ulrich, maybe a next question for you. Maybe I don't know if this comes under our scope. Where to check applicable silicon bugs?
Yeah, the silicon bugs are documented in the errata sheet or CPU functional problems list provided by Infineon. So you will need to have access to the MyICP website, which is password username and password protected, and then if you got access, then you can download the errata sheets for the derivative you are using, including the stepping you are using. In example, a TC27X EB or whatever stepping. So then you can locate the errata sheet for that derivative and read through all the known silicon issues.
Okay, thank you. Next question: can we use linker label address in LSL file and not in the C file? So can the linker label address be used in LSL file?
Maybe I need to understand the purpose. So typically you are using the linker labels to be able to access an address which is not known at compile time in your application code. So if you want to figure out the start address of a specific LSL group or the end address of that group, then you can use this linker labels. Yeah, they are defined in the LSL file, and they can be referred to by the C application using this linker label prefixes. Yeah, it's then depending on the use case what needs to be done with the labels from within the LSL file. So I would need to know more details here.
So I think for the next question as well, we may need a little bit more detail. I used RO data with wildcards in a group, but still one RO data.variable did not end up in the group I wanted. What could be the reason that it did not end up in the group I wanted?
Yeah, the most common reason is that it's assigned to another group. So the linker processes the LSL file from top to bottom. So first come, first serve. If this raw data section is selected in a previous defined group in the LSL file, yeah, then it will end up in that group. And if there is later on another select, which would also match the name of the section, yeah, then this select won't work anymore. So this kind of issue can be verified in the map file. So you can, when you always use group names, which is a good choice. So you can use unnamed groups, and you can use groups. You can give every LSL group a name. And if you add a group name to every LSL group, then you can benefit from the map file information, because the locate results section includes a column which shows the group name. And then it's very easy to figure out, okay, I know the section name, and I want to know which group includes this section, and then you can simply search for the section name in the map file, and you will, in the locate result section, you will see the group name, and then you can, then you know at least to which group it is assigned, and then you can review the LSL file to figure out whether there is maybe a wrong order used in the section assignment. And when there is no section name, then it's either assigned, when there's no group name, then it's either assigned to an unnamed group, or it's not assigned to any group at all. Then, of course, it's more, then of course there must be a different reason about why this assignment did fail. Another possible explanation is your group is defined in the wrong section layout. So you have a section layout for the near addressable sections, another section layout for far addressable, or so-called linear addressable sections. And this can all be in the virtual core space, where all tri-core cores are thrown into one space, or in the core local space. So if you define a core local variable like _private1 with this prefix, then it will be assigned to the core local memory of core 1, and then it needs to be selected in a section layout which uses TC1 for core 1, and not in example TC0 for core 0 or VTC for virtual core. And the linker does not complain when it does not match. So when the linker notices, okay, there is a select for a section which does exist, but it's in the wrong section layout. So yeah, I don't have to follow that requirement, but I also will not complain about it. So you will not get a notification when this user error occurs.
Okay, so maybe this is a quick question. Does license hosting strategy affect build time?
No, the licensing system is not is completely decoupled from this topic. So technically, if we are talking about a floating license, then yeah, you don't have an intense interaction between the client PC where the compiler is called or the linker is running and the license server. So the license is simply cached for 5 minutes. So every 5 minutes, the client sends a heartbeat to the license server just to signalize, okay, I'm still alive and doing something. So please still reserve the license for me. And yeah, so there is no impact of the licensing system.
A follow-up question about the silicon bugs. Does this mean the documentation provided as a part of tasking help is not conclusive?
The silicon bug document details, they are provided by Infineon. So tasking is only referring to if the tools do support some mitigations for known silicon bugs, then this ends up in our user manual, because you need to be aware of the compiler or linker option you need to apply to mitigate a selected bug. So we refer to the bug number in our documentation and maybe a brief one sentence description of the issue, but nothing more. So all the details, they are provided in the errata sheets from Infineon.
Mm-hmm. Okay, so that brings us to the last question regarding the memory overlay use case explained today. Actually, TRICO itself supports overlay feature at its hardware level. Then why do we need to explicitly define RAM sections in the linker file?
I think these are two different topics. So this overlay feature in the TRICO supports by hardware is if you want to map some data to RAM in order to from flash in order to modify them. So I'm not that familiar with the hardware overlay feature, but the tool overlay feature is for the purpose that you simply, if you need to execute application code in RAM memory, yeah, you need to locate it in flash somewhere, because it needs to be copied to the RAM location, and the purpose of this overlay feature of the linker script language is then that yeah, you can instruct the linker to create the ROM copy of that section, which can be placed or which will be placed somewhere in flash. You can also specify if you want to have an exact address in flash memory where the ROM copy is located, and then you can use the linker labels to create a copy loop which copies this ROM copy section to the RAM location anytime you want during application execution.
Yeah. So maybe I can also add to Ulrich's point. So a typical use case, you could imagine that, you want to load some of the, let's say, Infineon specific flash driver functions into your RAM, because you want to reprogram your flash, because you cannot run your code from flash and reprogram the flash. You have to run the code from the RAM to be able to reprogram the program flash. And in this case, for example, you can then you can have an overlay and map your flash routines on the flash to a memory, and then copy it into the memory at the time you want to. Basically, when you are at the point of at the time of before you want to reprogram the flash, and not all the time, because this could be then a safety error, safety related error. So this is one use case, just to understand the advantage of the overlay option. Okay, so yeah, with that, I think it brings us to the end of the webinar. And I thank you very much for your patience. And I also thank the presenters. And I wish you a nice day. Thank you.
Bye.
Goodbye.